This is Computing Up, conversations about computation writ large with Michael Littman and Dave Ackley. This episode was recorded December 21st, 2022.
Dave, what's a bomb cyclone?
Well, I don't think it's really anything, but people talk about it these days as if it's just a big storm that comes on really fast, and it comes on so fast, like a big pressure drop, that it's like a bomb dropped. And I think mostly it's just some stupid trendy name. So now everything's going to be a bomb cyclone, and there'll be bomb cyclone ice cream pops before you know it.
And when everything's a bomb cyclone, nothing is a bomb cyclone.
Exactly. And they'll have to come up with whatever's going to be next. I don't know.
But this is some weather that we might be experiencing.
Supposedly, much of the country is going to get like 40 degrees below normal weather over the next few days, and pipes are going to be bursting everywhere for Christmas Eve.
All right. Well, this is my segue then. So speaking of bomb cyclones, Chat GPT is all that anybody can talk about now. So either we should talk about it or we should absolutely not talk about it. But
that seems to cover the bases.
That's the extremes anyway. But I've been playing around with it, as a lot of people have been playing around with it, and it's really interesting because it does amazing things, and it's totally not clear how it's doing what it's doing, when it's just making stuff up, pulling it out of its digital butt, or when it's actually a reasonable thing. And it's like we need powerful machine learning techniques that you can actually understand what they're doing sometimes. I don't know what. Well, that's a lead into introducing Cynthia Rudin. Hi, Cynthia.
Hi. Part of the issue with these things is that they're not easily controlled, right? You can't control them to make them do what you want. They just sort of do their own thing, and troubleshooting them is very, very difficult.
Do we think the answer is trying to control them, or is that not the direction to even go?
I don't know. I guess it depends what you want to use it for. But, like I run the computational poetry team at Duke, and, we've been fighting GPT-2 for a really long time because it just produces what it wants to produce, and we want it to produce sonnets. And so, so just asking it to sort of rhyme and have the right rhythm and, so on. It doesn't want to do it.
Because it seems like controlling is always what we want to do, right? The whole point of building these models is to do something with them. If that thing that we want to do, unless they're just, alive, they're friends, they do what they do, we tolerate them. But that's a different thing. That's not why we have computers.
Well, you see, but that's what I wonder, I guess. Sure, if we're doing top-down engineering, saying I want to do a loop and I want to count by 1 and then multiply by 2 and compute the factorial, whatever it is, okay, yes, we want to control it, we want it to be top-down. But if we're trying to do something that's going to be more like, I don't know, an intelligent interacting assistant or something like that, I wonder whether to continue to have that sort of top-down control mentality is now being more like the sort of thing that you would do to a friend, and it might not be the best thing to do. I don't know whether I'm just completely missing the boat, but I do all this bottom-up engineering stuff. So for me, I am trying to build systems that go together well in some sense, that things that make sense to this compensates for that thing and so forth, without even knowing what the end use is supposed to be. There's some vague, fuzzy notion. And my goal is to sort of make stuff that will land cleanly, that will land on its feet. That kind of thing, sort of independent of what we want it to do. And I don't know, it seems like it's a pull from both directions, which is the only reason I was raising the question about control with Cynthia.
Well, I generally like my computers to do what I tell them to do or to do what I want them to do. So I guess my application's different. There's nothing wrong with generating a friend, right? I think that could actually be very helpful for a lot of people. It's just not what I'm personally trying to do.
Then they were saying that like there's some kind of distinction between people and computers, or there's some kind of distinction between the use of computers as tools versus the use of people as people, or something like that. And right or no?
I don't know.
You're looking at me like I'm crazy, which I'm not saying I'm not.
The use of people as people does feel a little antisocial. I don't think you meant it that way, or maybe you did.
I didn't want to say the use of people as tools because that sounded worse. But what I meant was the idea of that every machine has some things that it does just because that's the way it's built. And we would like those things to collectively be useful for whatever machine purposes it may have. But in the end, it's going to do what it's going to do because of the way it's designed. And it seems to me that people machines or animal machines, meat machines aren't different than computing machines in that regard. It's all one class of sort of, non-deterministic, sort of gushy machinery that we're trying to have it be useful and robust and all that kind of stuff.
Well, why don't let's give Cynthia a chance to kind of lay out her worldview, and then we can sort of compare and contrast.
All right.
So Cynthia, so what we've done a lot of these conversations. This one went in a funny direction I was not expecting. But okay, so just to introduce, so Cynthia Rudin is our guest today. Cynthia, thanks for being here.
Sure. Happy to.
Sorry.
Cynthia, no. It's I'm glad you're excited. So Cynthia's a computer science faculty member at Duke University and recent winner of the Squirrel AI Prize, I think it's called. And her work is very well regarded in machine learning and algorithms. And one of the reasons that I like Cynthia's work so much is because I am kind of frustrated about the computers, especially machine learning's use as a tool, that it's difficult to tell them what to do and to tell them and to see how they are doing what they're doing. And I think for many applications, it leads to a lot of concerns, right? So if we're talking about a system that is doing medical diagnoses or making judgments about sentencing for criminal activities and so forth, that people do it and we can't really see transparently into their minds how they're doing it, but we have lots of other ways of trying to vet people. And these machine learning algorithms that are just kind of giving an answer don't allow either thing, right? They don't allow for the transparency of understanding how they're doing what they're doing. And you can't really talk to them and get to know them and, get the cut of their jib to see if they are reasonable, judges, as it were. And so Cynthia, can you tell us a little bit about your perspective on some of these things and how you go about, like how you came to think about it this way, or whatever, how you think about it, how you came to think about it that way, and how you see the world moving forward?
Sure. So, I sort of was propelled into high stakes decisions pretty early in my career, right? Because I was working with the power company in New York City, trying to predict power failures in Manhattan and in other boroughs. And we realized that, designing bigger and fancier machine learning methods were not helping us get any more accuracy. What was actually improving our accuracy was understanding what we were doing, fixing problems with the data, and just, data science, like real data, grungy data science, right? And so I finally just said, the whole field is not working for me. Like, I don't understand this field. I'm not getting any, I love the elegance of all these methods, but they're not getting me any accuracy boost. And so I started working on models that were more understandable rather than models that were bigger and fancier. And, so while the whole machine learning world was going toward bigger, fancier machine learning methods for bigger and bigger data sets, I was looking at sort of more understandable, smaller models for high stakes decisions. And what I noticed was that, you have all these situations like data sets where, all these machine learning methods are performing the same, but they're producing very different answers from each other. And so I realized that, this is probably because there are a lot of different machine learning models that perform very similarly on the data set. And so I thought, look, okay, if that's true, if there are just lots of good models, maybe there are good models that are also very, very simple. Like, what if we really heavily optimized for simplicity? So you keep the accuracy. So don't sacrifice accuracy. Just aim for simplicity, subject to the constraint that your accuracy is just about the same. And what can you do? So I started working in a lot of these, very optimization-heavy approaches to machine learning. And we eventually, with the help of Margot Seltzer and a lot of my collaborators, we were able to design machine learning methods that produce these tiny little models that are just as accurate as these big fancy models. And now we can optimize them in kind of a reasonably small amount of time so that you can get, say, a decision tree on like a tabular data set in, a few seconds or a few minutes, even if the data set's really big, and the decision tree can be like really tiny, like it can fit on an index card and it can still perform as well as like the best random forest or whatever.
And it's
on the data set.
So it's inspectable, right? You could actually look at it and say, oh, okay, well, I see the rule here.
Yes, exactly. Yeah.
So you're saying that what I was immediately wondering was, well, how do you decide what the definition of simplicity is? And it sounds like what you're saying is you have some output representation, like a decision tree or whatever it is, that's going to have number of nodes or number of decision points or whatever it is, as a sort of natural measure of simplicity. And you just want to minimize that while still solving the problem as well as anybody. Is that the way it goes?
Yeah, so for tabular data, sparsity is a really good kind of proxy for interpretability. Obviously, it's not the only measure of interpretability. Like sometimes I show you a sparse model and you look at it and be like, oh, I don't like that model. That doesn't make any sense.
Right.
And so what we've been doing now lately is trying to not just give you one sparse model, but give you all of the sparse models and a good way to search through them. So Margot and I and our group of students have been working really hard at building data structures that store lots of these little tiny models and building beautiful visualization tools so that people can kind of look through all the models and find one that they actually find interpretable, even though they're accurate and they're sparse, but now they can look through all of them and pick out one that they find interpretable. For other types of data, though, interpretability means something different. So, for example, with visual data, interpretability. No, sparsity it doesn't really work. It doesn't really make any sense. And so we've been doing kind of case-based reasoning for visual data.
So is that the proto-PNet that you guys were working on, or is that like way beyond that now? I read that paper with little patches of duck-billed woodpeckers and all that sort of thing, and I thought it was really great. And is that a case-based thing, or is that yet another thing?
Yeah, that's the thing, that proto-PNet. Yeah, this is Chao-Fan Chen. This is a paper that we've been really expanding the use cases for it. So we've been working on computer-aided mammography, and lots of people have applied that technique to lots of different things. So it's kind of like k-nearest neighbors, but it's like k-nearest parts of prototypical cases.
Oh, interesting.
And that one is ultimately driven, if I understood it, by you've got the output categories. You've got the different things that it might be. And that's the K that you're asking, what am I nearest? Or is the K the individual parts of a wing and a beak and all that kind of stuff?
Yeah, it's the number of comparisons you're doing is sort of K comparison. So you have K prototypes, and you're comparing like the wing of your current bird to the wing of a prototypical bird from this class, and you're comparing like the colors on the bird's head to the colors on that prototypical bird's head. So it's sort of 20 comparisons or however many prototypes you choose.
Right.
So it reminds me a little bit of like vector quantization, right? Where you have kind of a library of examples and you're saying, I want to build that library so that there's a bunch of things that are close to what I'm actually going to see in the data, right?
Yeah, except ours is supervised. Yeah.
Oh, good point. All right. So supervise, because it's supervised in the sense that there's an output label that matters.
Yeah.
But you're not supervising the parts, right? You're not saying here's a data set saying what the parts of the bird should be.
No, where that is all all done by the algorithm.
So the fact that it's important to have the wing texture and the beak shape, that it's figuring that out. You're not giving it that level of stuff. You're just saying there's a bluebird and a red bird and a parrot and so forth.
Yeah, we don't even tell it what prototypes to use. It has to figure all that stuff out by itself. And sometimes it picks out things that are just sort of, I don't know, I guess what we'd call confounding information. So sometimes, for instance, with, if it's classifying water birds, it'll pick out a prototype which is just water. And so you'll be like, oh, I'm not sure I want it to do that, but it's leveraging the information about water to right. classify the water birds. So you got
to admit that it often goes with the water birds, but you had this prior notion that you wanted inside the feathers, not the stuff from outside the feathers, like that, and that's hard to express.
Yeah, but the nice thing about it is that you can go and look at what it's doing and say, like, I don't want you to use that prototype, and just you can knock that prototype out. So
uh,
you can force it to you can force it, you can troubleshoot it. It's just much
Yeah.
easier to
and how do you
troubleshoot than
know?
a standard
Because
learning model.
it will come up with its prototypical patches. It will say, here's the wing patch for the woodpecker. That's what I'm leaning on, and so forth. So you're going to look at it and say, I'm sorry, that's lake. We don't want lake. And now put an X in there and train some more or whatever it is.
Exactly.
So
You can
Cynthia,
say like, yeah.
okay. So this means to get a good answer out, there's people input in yet another place in the pipeline. And I remember, so I was working on some reinforcement learning problems, and I had a student who said to me, I want a person to be able to have input here. And I'm like, no, that's cheating, or it's like, that's not in scope. And he slowly wore me down until I came to admit that actually there's always going to be people involved. And if we're developing algorithms that are going to produce answers that matter, maybe it's okay to, like, we want to make people involved in a way that they can be most productive. Is that sort of how you see things as well? Because I think a lot of people would call it cheating.
Oh, I don't think there's even a question there. I mean, we're trying to build an algorithm for computer-aided mammography. If that algorithm is not solidly built, then it's going to classify breast lesions incorrectly. So if you've got an algorithm that's looking at this part of the healthy tissue over here to classify the lesion that's over on this other part of the image, there's a problem. So I don't see any reason why we can't use our radiologists to help us improve the quality of this thing. So I don't see the way, I don't see why you could even think about calling this cheating. That's not in the realm here.
Well, I mean, the point is it has to be disclosed, that you have to say that here we did 3 iterations with an expert and pushed away blah, 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 or else it seems like you could just be doing mechanical Turk all over again. And the machine learning would just be the window dressing.
Oh, we tell, you know what? We even, so we had a problem where the algorithm was looking in the wrong place of the image. And so we changed the whole algorithm so that it could incorporate specific like location labeling from the radiologist. We actually wrote a whole paper on how we incorporated the radiologist's expertise into building the better algorithm. So yeah,
Well,
it's
so
not like we didn't report it.
Exactly. As long as it's disclosed, then it becomes a feature. The worry used to be that, in the early days of machine learning, which means that the 80s for me, the whole point was that you did something hands off, that the machine did it itself.
Yeah.
So we all got trained that, can't touch the test data, and so forth. And I think that's what Michael was echoing. And to say that, but we actually want useful results, then there's going to be hyperparameters in the front and there's going to be some model rejection at the back, and we better admit that and try to do something sensible with it. And it sounds like you're way down that road.
You're hitting on this kind of old school, this is the reason why I had so much trouble throughout my whole career, is this old school notion that interpretability is actually something we really don't want, because we want the computer to do it all itself. We want it to really depend on the data. It's only data that matters. And it's like, well, your data has problems with it. Like every data set has problems with it.
Absolutely.
So why are you not letting me troubleshoot this? So there was this sort of like idea that it wasn't elegant, like that interpretability, that understanding the model, that having a human in the loop was totally inelegant. And I never felt that way. Like I always felt that because I could troubleshoot, it was more elegant, because I could see the model, because I could get a model that was so tiny and it was just as accurate as these big models, that it was more elegant. And it's been really hard to convince people over all these years that this is, this notion of elegance is actually, it's valid. It's
I mean, I guess one of the things I feel, talking about simplicity, is that, we think of, genius as the process of coming up with some singular nonlinear transformation, which after you do that, now everything is simple. like that. So it wouldn't be interpretable in terms of prior concepts. The radiologist or whatever it is would never have thought to do whatever, but then afterwards we go, aha, wow, that's incredible, like that. And the worry, I guess, is that if we chain ourselves to the concepts that we already have going in, which makes it interpretable, and I want to agree with you. I think being able to explain what you're doing in a way that the people downstream understand should be table stakes. But at the same time, I also sense the desire for, true intelligence or true amazing intelligence or whatever is this kind of thing where we wouldn't have known it until after we saw it.
Yeah, there's still also this sort of idea that like the computer is finding something that's so subtle and so important that no human could possibly understand it.
Well, I think
and it's
that's
like, well
cool.
then, well then, how do you explain the fact that I just got this tiny little model that's just as accurate as your who knows what that you can't really explain? Like, I don't get it, right? So often also you have this stuff that like you can't, that the computer can't really explain to you what it's found. And as it turns out, it found something that is just confounding information that you wouldn't want it to depend on anyway. And especially with medical stuff, especially with like radiology, it does it all the time, right? It does that all the time.
The name of the hospital on the edge of the image or whatever the hell it is. Stuff like that.
Exactly.
Yeah.
But I think from a research standpoint, I think people might struggle with the idea of, okay, well then what makes your approach superior? The game, the classic machine learning game is like, you give me a data set, I give you a classifier, and if I'm allowed to tinker with the insides of it, then that's cheating because I want a machine that's going to produce data in, classifier out. And you're saying, okay, no, that's a terrible idea because ultimately you're not going to get the best classifiers out. You're not going to get classifiers that people are going to be able to use to solve real problems. But then what's the new game, right? How can we have a competition between your idea and somebody else's idea? Or maybe that whole idea of competition is faulty.
Okay, so let's back up a second. So I'm doing the same thing, like data goes in and classifier comes out. Okay, the only thing that's different is that my algorithms are constrained, right? There's constraints, right? And maybe some human feedback.
Maybe some human feedback.
That's
feels
more
like
data.
You snuck in a smart person.
Hold on. So before I did that though, I noticed that in a lot of these problems, there are a huge number of almost equally good models. Your algorithm spit out one of those models. It just happened to be something I couldn't understand because you didn't tell it to pick out of these good models, you didn't tell it to pick one that could be understood by humans. I'm just telling it, pick me out a model that could be understood by humans. Then it picks out a model that could be understood by humans. And then what happens? The humans say, oh, I don't like this model because it depends on blah variable and I don't want it to depend on blah variable. So then we have to go back and pick a different one of those models, right? So that's the idea that, you instead of just picking out one model that seems to do well on the data, you're actually looking around in this space of good models and picking one out that, agrees with domain knowledge and that you can understand.
I mean, when you say interpretable, human interpretable, that's what you were talking about, simple before, right? Or is that different? Human interpretable, simple are the same or not?
Well, I mean, simplicity, like I said, is a component of interpretability. But for example, with the deep neural networks for visual data, those models are not simple, right? They're just as complex as any deep neural network problem. It's just that they're doing case-based reasoning.
The dimensionality of the latent space is super high. When you say complex, what is that meaning there?
So, I mean, the way we construct our interpretable neural networks is that we take your favorite convolutional neural network or whatever network you want,
and so on.
Millions of parameters, and then we replace the second last layer, right? We replace the second last layer and force it to do case-based reasoning. So you're keeping that level of complexity so that you can, solve computer vision problems, but you're just forcing it to reason about the image in a way that is case-based so that a human can understand what comparisons the algorithm is making between images.
And the humans were picking the cases, or those were the top N from whatever the machine came up with.
Machine has to come up with them. It doesn't do top end. It actually sort of optimizes which of the examples, the training examples to use as prototypes.
It decides how many prototypes to make?
No, the human says, oh, I want, give me 5 prototypes per class, or
Okay.
give me
All right.
10 prototypes per class. And it says, okay, we'll pick these 5.
I get it. And okay. So, all right. Which doesn't really get at what Michael was going on about where then now we have the human come in and say, well, I don't like the way you did that one. So pick from the numerous other equally good ones and so forth. And now we report the results. The human computer algorithm hybrid produced this thing. And the point I assume you're making is that, and now we can actually classify lesions with it and make decisions that are going to affect people's lives. And the point is it's a better decision because there was the radiologist in the loop pushing back against, whatever it was.
Yeah, so the computer here is now a tool again, rather than a decision maker, right? You really want these decisions to be computer aided and not automated, because you really want to keep the doctor in charge of their own patients.
Well, but it seems like the business people want to get rid of the doctor because that's the expensive part of the system from their point of view. It's a cost center. So there's this pressure to try and make it be a decision maker and not just an assistant.
And maybe we should push back against that, right? Because there's other ways of improvement, right? One way to improve is to have better health outcomes with the same people that you've got, but better health outcomes.
Yeah, it just depends on the complexity of the decision. I mean, if it's a really simple decision, like, I think there's a lot of code out there for just detecting whether there's anything in a mammogram at all, right? So you could build something that would just detect whether there is any kind of lesion in the mammogram at all. If there's no lesion and the algorithm's 100% accurate on this particular question, maybe that's going to save a lot of time. That's great. It doesn't need to be interpretable. But the questions I'm working on are questions that you have to train. A radiologist has to train to solve these problems for years. They are very complex, very difficult challenges. And you can't rely on a computer for these kinds of problems. Like even radiologists, like this is the hardest task in all of radiology is mammography. So,
right.
Yeah.
I mean, a lot of what this reminds me of is actually my first research paper from like 1985 or something like that, when expert systems were in their big heyday rage, or their first one, with backward chaining and if-then rules and the whole thing. And part of the mantra of expert systems is they're supposed to be able to explain their decisions. And they do that by unfolding the and/or tree and say, well, I needed to take temperature because then, blah, 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 and so forth. And I was working with Hans Berliner, who later became famous doing chess, but at the time he was doing backgammon. That's right. And he had come up with a backgammon program that had beaten the world champ in an exhibition match, although it got some really good dice in the process. It was still a very good backgammon player. And I, as a grad student, a brand new grad student, was tasked with making it explainable, making the backgammon program be able to explain why it did what it did, even though there was no if-then rules. There was no backward chaining. There was just a big ass evaluation function that got run on each possible result from the die roll. And that's it. There was not even any tree searching. There was just the half ply.
And that evaluation function was built by Berliner, or was built by
hand? It was built by hand by Hans,
no learning,
who would just sit there playing the program all day long.
It's a learning system. It's just a learning system that is a person.
Until it did something that he thought was wrong. And then he would go in and look at his evaluation functions and like that. And it got very, very
the
good.
80s.
It got very, very good. And the key to it was that he postulated these intermediate nonlinear terms, which he called application coefficients, that you'd say you've got all these terms like how well the running game is, what the pip count is, all of this stuff, aspects of the backgammon board. But then you've got these higher level things, which is like, how much do I even believe a running game is important right now versus how much do I think a blocking game is what we should be talking about. And those things, he had separate mathematical expressions to produce the application coefficient, which would then multiply by the sum of all the terms that were running related, and so on and so forth. So he was doing the hidden layers as well,
Wow.
in effect.
Building up a big neural network by hand.
Building up this essentially big neural network by hand, and realizing all the things that we have, again, really re-realized, that you can't have binary discontinuities. You have to have smooth things, which in effect, the requirement for differentiability, so that you can go back through it, was just in his head, because he would see that, if it's a hard edge decision, then, you would avoid going in that whole direction, even though it's inevitable. So you would start sacrificing all your pieces until then finally you went into the running game, and you were much worse off than if you had pulled the trigger to begin with, but you wouldn't have known that because you could push it over the horizon if it was this binary decision to believe it was a running game versus not. So anyway, so then just to finish this endless story, geez, sorry. The work that I did was, you'd say, okay, well, why did you do that move? It says, do whatever the move is. And the QBKG, query BKG, that was the name of my system. It would say, well, what do you think we should do? And so it makes you give us an alternate move. And then we would evaluate the two moves and start at the top of the evaluation tree and work our way down, looking for the big differences. Well, your move is better in the blocking game, but it's completely dominated by the advantage of this move in the running game, and so forth, and generating a little text, basically just unparsing the parse tree, the evaluation tree, which guaranteed that it would be interpretable to finally get to the point, because Hans had defined all these intermediate terms in terms of concepts like blocking game, running game, and so forth, like that. And so it just seems like a funny echo, Cynthia, that, that you're sort of bringing this all back again, except automating giant chunks of it in the process.
Right.
Yeah, I'm completely anachronistic. I don't know what's up with me, but when I hate to say it, when I was a high schooler, even back then, right? I was writing music, and the kind of music that I was writing was like century-old French music, or maybe 120-year-old French music, and I realized I couldn't actually have a career in composing because nobody cared about that anymore. And it's the same thing. I go into machine learning and start working in interpretability, which is like expert systems stuff from the 1970s, and everybody was like, "What the heck are you doing? We don't care about that stuff anymore." So.
Well, but they're catching up with you now. They're catching up with you now.
I think so. Yeah.
I was trying to remember so you and I haven't met, but I knew your stuff, and I realized that a big chunk of it was from Brian Christian's book, like that interpretability and everything, and simple models, all that stuff. Oh yeah, that was Cynthia Rudin, like that. So I think at least people who I respect as far as having their head on straight for where AI is and where it should be going and where we should want it to go, your stuff is playing an important part of that story.
Yeah, thank you. It was pretty frustrating, especially in around 2016 or 17, when, I've been doing this for years, right? Like really, really long time. And then all this explainability stuff showed up where they were like, oh, it's okay. We can use black boxes because we can explain them. We're okay. And, we can trust these models. We can trust the black boxes now because we can explain them. And I was just like, oh my gosh. So I just sort of felt like AI was sort of, I was over here, AI was over here, and then it sailed over my head to go somewhere else. It's just like, what the heck?
Right.
What's going on here?
We're going to kind of do a bank shot off of your stuff to say, it's also relevant to this, and then we're going to go in another completely wrong direction. Well, I hear you as far as being off the main line. I mean, if we're not talking about my work, but it's way off the main line. So I understand that feeling. But it seems to me you got to go for what Makes sense. You got to, I mean, to me, the point of doing research and stuff is to try to figure out where you can make a contribution that other people aren't making. And if that's because the herd is going in that direction, well, then so be it.
The field is just so like herdy, I guess.
Yeah.
It's so, bandwagony. I don't know how else to describe it, but there's these trends and they go,
Well, here's my theory. See what you think of this theory. My theory is that, everyone talks about fads and how silly everybody following the fad is. But my suggestion is, my fantasy is that in a parallel distributed system, fads are a great way to find the limits of an idea fast. So when somebody puts something out there that seems new, now everybody goes and piles in and they do a million different little variations on that. Stupid variations, smart variations, it doesn't matter. But the point is either the thing will stand up or it'll start fading out, and then we'll go pile into the next fad. And so that instead of focusing on the waste of having tens of thousands of researchers all submitting papers that sound exactly the same to NeurIPS, what we should be focusing on the little thread that comes out 2 years later that, generative networks are good for this purpose or whatever it is, and then the next fad moving on. What do you think?
Yeah, well, so the issue is that if you have the whole field working on this one thing that doesn't work, you just waste a huge amount of human effort. So I think about, my career. So it started out at the time when support vector machines were king, right? Support vector machines never really worked very well, right? And we now know why they don't work, right? It's because the kernel had to be the same everywhere, right? It was not non-uniform. And this is why boosting has now sort of been the method that takes over everything, because it was all adaptive. Everything was adaptive. So, you had, I remember every conference, every paper was support vector machine, new kernel for support vector. Some of them weren't even kernels. And I would walk up to people and be like, excuse me, do you know if that's a real kernel? And they'd be like, what are you talking about? It's just a way of comparing things. I'm like, no. Okay.
That's
so
not
anyway.
what a kernel is.
Yeah, yes. It's it's got to be in a product and a reproducing kernel, Hilbert space. No, anyway. So, you had tons of people doing this nonsense there. And then it was this whole non-parametric Bayesian stuff that were so difficult to optimize. And just, I don't even know if people are still doing some of that, I don't know. But so you had all these people doing this stuff. They're not doing it anymore. And then it was this, and then it was that. And now it's explainability, right? Instead of interpretability, like explaining black boxes. And I'm thinking, look, if we just had people working on real problems, right? If we actually had people working on real problems, they would decide themselves what the important problems in machine learning actually needed to be and try to solve those, right? So that's, I don't know. But the problem is you've got, NeurIPS, ICML, all these conferences, they don't accept applied papers. And so you can't have the same people working on applied problems as working on methodological problems. So I've been kind of railing on this, the machine learning world for years to try to get them to accept applied papers so that researchers could do both applied and methodological research. But, it's not... I have not been successful as of yet, although
and there's no other places to go. I mean, I'm out of machine learning at this point, well, for a couple decades. So there are no prestigious applied places that would vacuum up all that sort of stuff.
So KDD always had an applied track. The problem is that they always the methods had to be deployed, which basically meant that you couldn't do anything in medicine or in science because, or in the arts, because you can't deploy that stuff, right? It had to be like advertising or whatever. So this year, so I'm on the SIG-KDD board, and this year we totally changed it. And so this year we're going to accept a much broader variety of applied papers, but it might take a little while for it to catch on. But now you also have the problem that one of the main ranking systems for CS conferences has now taken out KDD and replaced it with ICLR, which now I'm like, oh gosh, what are you guys doing? So
that's because KDD had a whiff of actual applications. Is that why they got kicked out, or nobody says?
Something, I don't know. I have a feeling that all the computer vision people have been controlling the field for so long that I think a bunch of them were submitting papers to ICLR and then complained to the rating systems that ICLR wasn't being
I see.
contained in there. So yeah, our field just always had these like massive cultural issues that, you know, with the review quality, right? The reviewers laugh at papers that are applied papers. They just, they
Yeah.
told me we had a paper last year. They said, "Oh, your paper is more like a blog post than like an applied paper."
Yeah,
I'm
it's
like, I have these
way
famous
too
scientists on this paper.
understandable. Yeah,
Oh,
like that.
yeah.
I hear you. I
So,
mean, yeah.
yeah.
Well, yeah.
I mean,
Go ahead,
one
Michael.
of the I was going to say one of the areas that I thought you guys would definitely agree on is the importance of looking to see what the system actually does, and not just being happy to stay in theory land and say it doesn't really matter. We don't have to be connected to the real world in any way. I feel like both of you have expressed, maybe in different ways, but both of you expressed that idea that without being attached to something that actually matters, you're just goofing off.
Yeah.
Yeah, I agree.
Yeah,
I agree.
and it's possible certainly to be too applied and to refuse to lift one's nose out of 27,000-volt feeders and hammerhead T junctions and so on and so forth, and refuse to see any bigger picture at all. So you have to actually find a way between, and I understand that, but I feel like the pure theory end of it is the bigger sinner in these things, like that off in thermodynamic limit, off in infinite time limit, off in assume it's linear, all of that sort of stuff, and not touching applications at all, and finding that middle balance is the hard part, and that's kind of the point. That's where the breakthroughs, I think, can lie.
Yeah, and I keep speaking out about this issue at places like this, right? And at other places. I'm really hoping that at some point somebody, who has the power to make a change notices, right? I mean,
Yeah.
like I said, we're making a huge change at KDD, right? But we'll see if that sort of propagates to sort of central machine learning. I don't know.
Right. Yeah, I don't know, and I certainly haven't been to NeurIPS since it was NeurIPS, like that. But just looking at the size of the rooms they have, it's like that's not the NeurIPS I remember, and so I can easily see the cynicism of looking at the herding behavior and saying, "My God, there must be a better way to deploy all this incredibly expensive human talent," but then. I don't know.
I mean, I wonder. I don't know I don't know who even studies this stuff, but like, are other fields so fatty? Like the fattiness is really notable. And Cynthia, you did a nice job of kind of laying out at least two of the maybe 7 distinct fads that I've seen since I've been around this field. Dave, I understand the idea that, okay, well, there is some potential adaptivity to this way of structuring the search for good ideas, if you want to think about research that way. But what does chemistry do? Like, do they get all crazy like we do? Is it they're not too attached, but they're attached to the science in a way that doesn't let them go off in these wacky directions?
I don't know, but I would bet that the real science, anything that doesn't have to call itself a science, like computer science, is generally anchored around techniques. It's oriented around technology. When PCR comes out, all of a sudden there's this huge flood of taking advantage of PCR. When CRISPR-Cas9 came out, all of a sudden a gigantic flood like that, because it made new observations possible. And people then want to say, well, generative adversarial networks is like CRISPR. It's a new technology, which then people just kind of pile into and find the limits, find the corners, like that. And so, I bet there's an awful lot of PCR papers or whatever the hell, the Diels-Alder papers in the 1800s, I don't know, that were similar, where chemists were going nuts. I mean, because people aren't that smart. If there's one good idea, everyone's going to try to jump on it and get, catch some money while it's raining money. Like that. Well, is that too cynical? I don't think so.
No, I don't think so.
And so maybe we're no worse, Michael.
I hear you.
And at least, sometimes we deliver software, so like we could go talk to the philosophers, they don't have anything. They published the paper and they thought they were done, like that. So,
well, one thing our field has done a really nice job of is sort of changing the culture so that things are reproducible.
yeah,
I mean, it's not always, like very often in some of the really hot fields, you try to reproduce something and you realize, they didn't make their code publicly available because they wanted to sell it to somebody else, right? That's pretty frustrating. But in general, the default is that the code should be publicly available. And I really like that. I think it's a nice thing about our field that you could just, you could say, no problem. You want to get code from our paper? Here's the link, right?
Yeah,
it's publicly available.
It's been available the whole time. And you can go look at the development history and see blah, blah, blah. I mean, it seems to me that's sort of still developing. That feels relatively new to me, the last 5 to 10 years, that, conferences are insisting on artifacts and all that kind of stuff. And I think it's a great thing. But it seems like maybe we still even have a little ways to go.
Yeah, but what I feel like Cynthia is saying is that there was a culture change, and that's encouraging, right? Because it's arguably a very positive culture change. Maybe there could be other positive culture changes too.
Yeah, I hope.
Hope springs eternal.
Well, so if you were the emperor of reality and you had the opportunity to direct the herd in its next pell-mell, which direction would you focus it?
Oh my gosh, societal good. Geez, I would focus it on applications that would help people. We have so many tools and there's so much data. And there's a huge communication gap between that data and humans. And so, if we could have people working on real problems that would help us, help us solve those problems, but also bridge that gap so that we could have more problems be solved, then I think we're going in the right direction.
So what's your advice to researchers then? Like it's hard to work essentially in someone else's field on their problems. You have to really roll up your sleeves. And is that real? Is there a shortcut to that, or
yes, get a collaborator. Get a collaborator who knows the field.
That sounds hard too.
Oh no, anything but that.
Oh, really? Is it that hard to make a friend?
I went into science so that I didn't have to talk to people.
I met Dave in the 80s, so I never had to meet anyone else.
They all want to do machine learning. The whole world wants to do machine learning right now. The whole medical field wants to do, all the medical fields want to do machine learning. All the scientific fields want to do machine learning. And they're all really smart. They're even training themselves to do machine learning. Half the students in my class are from all over the university doing something else, right?
That's
they don't want to do it.
So tell me, what does the first month feel like when you're working with someone? Because my experience, at least decades ago, in trying to work with people who actually understand the problem that they want solved, is that there's this huge conceptual and terminological gap, and there's this very long period of time when nobody understands what anybody else is saying. And so how do you make it through that period?
Well, so it depends. I mean, if you have one or two students who are dedicated to understanding what's going on and being able to communicate with each other, it makes things easier. It's someone's full-time job to sort of bridge that gap. And they bridge it fast if you've got somebody who's smart,
I see. So they're really dedicated, and they believe in their heart that if they just stick with it long enough, something really good is going to happen on the other side. Then you can make that bridge.
Yeah, I mean, the catch is to find a collaborator who actually, wants to make an investment, right? Because for them, they have to, they're going to have to get a data set, right? And they're going to have to construct a data set, and they're going to have to understand what the problem is that data set is going to solve. And so it's a lot of work kind of on their part, not just your part, but their part as well. And so, just finding a person that you can bridge that gap with is hard. But the thing is, though, once you get that person, if you've got a good collaborator, you can keep them forever, right? I've figured that out because I have collaborators that I've been working with for 10 or 15 years. You know what I'm saying? So, my neurologist collaborator, Brendan Westover, I've been working with him for ever, right? So, and we've written so many papers together on all different kind of important neurology problems. These are critical care patients. These are patients in the intensive care unit who are having monitors hooked up to their heads, and the output of these monitors is, read. It feeds into a machine learning algorithm, right? So, and he knows machine learning well enough now that this is nothing for him. And I understand what he's saying well enough that it's like, oh yeah, okay, now I know what you want to do. Let's bring in these are the students who need to be working on this project. So yeah, it's a relationship that you have to make, but it's not hard, honestly.
That's awesome.
Well, I feel like maybe this is just the old person talking, but it feels to me like in the era of the internet, the last 20 years, the kids growing up are actually much better at getting along with each other than I used to be when I was a kid or equivalent age or something like that, which I attribute to everybody pounding the crap out of each other in MySpace or whatever the hell it was when they were in middle school and learning how to get along with each other, which I think ought to pay dividends in being able to have collaborations more quickly, be able to ramp up more effectively. So, in addition to, grad student springs eternal, and that's the great thing about them, they're just all full of beans and you can point them at some impossible problem and they don't know it's impossible and they go do something like that. There may be an actual improvement in how people are able to get along and be able to get around that language mismatch and stuff that Michael was talking about a little quicker than in my generation. Maybe. I wonder.
Well, you also have a lot of people from across different areas wanting to learn machine learning, like I said. So you have students who actually have knowledge of both topics.
Right. Yeah.
Yeah.
Well, certainly, Cynthia, I hope I wasn't too, I don't know, aggravating, but I really enjoyed this talk. And it seems to me if we take what should scientists be doing, and the answer is collaborate for social good. That sounds right to me. That sounds like a great
argue
place.
Against that.
A great place to let it go for today. So thank you so much for talking to us today.
Oh, my pleasure. That was fun.
This was Computing Up. Thanks for listening.